No, so this is an integral that I'm going to use a method to do this integral. I'm going to use a method called trig substitution. So you don't know how to do this integral. So you can act like you do. You can shout out suggestions, but you cannot do this integral. In fact, this was the integral that popped up. If I had bounds on here, I really don't want to put bounds on here, but if I had bounds on here, this was popping up last chapter, and we said, oh, we couldn't do this integral, and we would use geometry. We would say it's a semicircle, and I'm integrating from -3 to 3, and it's the area underneath it. This is a semicircle of radius 3, and I don't know if you remember those. So we would just shout out the answer because we couldn't do it. But I'll teach you how to do it, and I need you, and without bounds, you have to do it anyway. I guess you got to try to do it. So we do it with this trig substitution. Check this out, man. This is cool. Instead of U substitution, it's trig substitution. So I let x equal 3 sine theta. So I'm going to be changing these variable x's. I'm going to be changing them into thetas. The new variable is going to be theta instead of x. It's kind of like when you change x's into u's, you're changing the variable, but I'm changing x's into thetas. And everything's going to turn into a bunch of trig. Now, if you're going to let x equal 3 sine theta, then the first thing I think I need dx. So you know how to do that. You walk in here and you take the derivative of x and you call it dx. And then you take the derivative over here, which is 3 cosine theta d theta. Is that bothering you a little bit? You should know how to do that. Listen, if I wrote u equals 5x cubed and said find du, you would 15x squared. I mean, you know how to, when I do a substitution and change variables, I need to do the derivatives, and so that's what I'm doing here. I took the derivative of x, it's a 1 dx. I took the derivative of this, 3 cos theta d theta. And then I substitute this all back in. Watch, and it's beautiful. See, the problem is, what you're dealing with here is a square root that you just can't integrate this nasty square root. And this fancy substitution we're doing will fix that for me. Watch, you'll see it happen. It's going to be beautiful. Here we go. So this is a 9 now. What am I plugging in for x? 3 sine theta. But now I am going to square it. So
it's be 9 squared theta.
So it'll be 9 sine squared theta. That's my 3 sine theta squared. And then so that's easy. And then there's a dx out there on the end. And what does dx get replaced with? What is dx? It tells you right there. What is dx? 3 cos theta d theta. So 3 cos theta d theta. So we just turned an algebra problem into a trig problem. And the point was to sort of get rid of this radical. And maybe you can see, maybe you can't yet, but watch how this radical cleans up. What you do is you factor out a 9, but the 9 is still in the radical, but you kind of factor out the 9, leaving 1 minus sine squared.
Which is cosine squared.
1 minus sine squared is cosine squared. So we turn this into 9 cosine squared theta. And now, can you do the square root of it?
It's going to be 3 cosine theta.
It's going to be 3 cosine theta. Now, I kind of got excited there and lost track of the rest of my crap, but I started cleaning up the radical, and there I am. The radical's gone. The trig substitution gets rid of that radical for you. Now wait a minute. Let's not lose track of everything. This was still out here, okay? So I'm still multiplied by a 3 cos theta d theta. There's still an integral symbol out in front of this. So now I'm integrating this, which by the way is a 9 cosine squared theta d theta. So I sure am glad I studied section 8.3. Because in order to do section 8.4, what you're doing in section 8.4 is you're turning these integrals into trig integrals using trig substitution. And so then you're turning them into trig integrals, and now this is why we studied 8.3 before 8.4. We learned how to do this in 8.3. You with me? I mean, we did, but it was just 30 minutes ago. I mean, we didn't. So I know how to do a cos squared. There's only one way to do a cos squared. You use the half angle formula. You don't do odd man out. You use the half angle formula. I'm going to pull out the 9, and I'm going to rewrite this as 1/2 1 plus cosine 2 theta. I'm going to go ahead and pull out the half. That's a 9/2, and then I'm going to integrate, you guys. Can you integrate a 1, please?
Theta.
Theta. Can you integrate a cos 2 theta? Okay. So that when you integrate a cos 2 theta, it's just a sine 2 theta. It spits out a half, though. Ta-da! We're done! Woohoo! We're done! Wait. We're done, but we're in thetas. Right. Don't we should get back to the original problem was in x's. So we got to get these things back to x's. And that's a bit tricky. So hold on just a minute. One of the tricky things about it is my original relationship between x and theta is right here.
What if we solve for theta from
My original relationship between x and theta is right here. And I might want to play with this a little bit. Yes, you're right. But one problem over here is that this has got this sine 2 theta. That's bugging me because I got this single theta here, and over here is a double theta. Anyway, but you're right. I could play with this. I could divide by 3. X over 3 is sine theta. And if you wanted to know what theta was, what's theta?
It's the arc sine of x over 3.
Yeah, it is. It's the arc sine of x over 3.
Yeah.
I mean, these are true thoughts. These are true thoughts. I mean, this is divide by 3. And then if you want theta, you take the arc sine of both sides, maybe. When we do this problem, there could be sines and cosines and tangents and all kinds of stuff over here. So one really beneficial thing, I'm going to advise you to do this, is draw a triangle for your angle theta. Now, I can't really draw it from this statement, but I can draw it from this statement. I can draw a triangle right here. Watch. I'm going to draw a right triangle. I'm going to put this angle in here called theta. Now, watch. What's the sine of theta? The sine of theta is x over 3, opposite over hypotenuse. I'm going to put opposite over hypotenuse. I'm going to do Pythagorean Theorem to get the other side in case I need the adjacent side. Pythagorean Theorem would be the hypotenuse squared minus the other side squared, square rooted, so the
square root of 9 minus x.
So it's 9 minus x squared, which showed up in the problem, which that's not a coincidence. That tends to happen there. That expression's in the problem. So I think I'm going to need this, but the truth is, this is a picture for theta. What's bugging me in this problem is I got this sine of 2 theta, and I don't have a picture for 2 theta. I don't have anything about 2 theta. I wish I could get rid of 2 theta. You know, there's a double angle identity.
Right.
So here comes another identity. The sine of 2 theta is 2 sine theta cos theta. I'm going to use that. I'm going to need it. I'm going to need that. It frequently happens in this particular problem at this particular moment. I have this sine of 2 theta, and I don't want a sine of 2 theta. I'd rather have that. So I'm going to change this here. This is theta. This is 1/2, but when I replace the sine 2 theta, it's 2 times sine theta cos theta. So the 2 and the 1/2 cancel. You guys okay with that? And then I want to, like I said, we're trying to turn this all back into x's. So here we go. I'm going to try to turn this back into x's. Let's see. What do you think I should call theta?
Up there. Arc sine x over 3.
Theta.
Arc
Theta
sine x
is
over 3.
the arc sine of x over 3, right? That's theta. So theta is the arc sine x over 3. Then I come over here. That 2 and that 1/2 cancel. So now I want the sine of theta.
X over 3.
And I could look at my triangle that I drew. What is the sine of theta?
X over 3.
Opposite over hypotenuse. But the truth is, I didn't really need the triangle. Earlier, right there, what's the sine of theta? X over 3. I mean, I didn't need the triangle for that. It's right there. The sine of theta is x over 3. So now I need the cosine of theta. Okay, what's the cosine of theta? Well, that's not, I don't want to go there. It's not anywhere. But if I look at the triangle, I can do anything from this triangle. I can do the tangent of theta, I can do the secant of theta, I can do anything you want from this triangle. Anyway, what's the cosine of theta?
Square root of 9 minus x squared over 3.
Adjacent over hypotenuse. Adjacent over hypotenuse. So this square root over 3.
Oh my goodness.
And we're done. We're done.
That's all you gotta do.
That's all you gotta do.
You guys know what you're doing. That's it.
Simple.
One question.
Again, you can stop here, but if you did distribute, things do clean up a little bit. Like, you know, this 9 would cancel with this 9. This is a 9 over here. But I don't really care. Remember, I'm so damn happy you get here. I'm not grading whether you can distribute a 9/2. I don't care if you can distribute it. I mean, if you do it wrong, it'll cost you a point. But anyway, I hope you can. I'm teaching you these integration techniques. I'd like you to fight through these integration techniques, and I'm not too concerned about cleaning up at the end. I don't even care. I mean, this is good.
So I have one question.
I do too.
All right, go
Where
ahead.
did you get x equals 3 sine theta
Yeah.
from?
Well, yeah.
Does it come from the 9?
Yeah.
In the square root, and then that sort of looks like.
Well, yeah, I got to give you some notes, right? Remember I said, I'm not giving you any notes. Let me just do a problem.
Yeah,
So I just did a problem without any guidance. I mean, you're right. At the beginning of this, how did I get started? Well, I'll teach you that. I guess you just sort of memorize some stuff. Any other questions? Right, here's the notes for section 8.4. The notes say this. The book says this. What you'll be doing is you'll be running into integrals that have an a squared minus a u squared inside a square root, most likely, although there are exceptions. So I'm going to write down some rules here, but there's exceptions to these things. But anyway, if this is the expression you're looking at, by the way, when I write a, it's a constant. When I write u, it's a variable. Okay? There's no argument with it. A is never x's. U's are x's. A's are numbers. But when I have this scenario, which was my scenario, do you agree? Then this is the substitution you should make. And you let u equal a sine theta. And I think you should kind of memorize that. I mean, you could ask me, why do you do that? The reason why you do that is because plugging an a sine theta in there will clean up that radical. I mean, the answer, why a sine function here, is answered if you follow these steps. The reason I put a sine function in there is because look what happens with a sine function. Bam, it cleans up the radical. Okay, what if it was different? What if it was an a squared plus a u squared? Well, then those identities don't work, and I need a different identity, and so now I let u equal a tangent theta. It's a different trig substitution for a different format. Why this one now? Because if you plugged it in, the identities would work out to where this radical cleans up. With this substitution, this radical cleans up. It's a different radical. That substitution won't work with this one. Here's another one. Again, you know the difference between u and a. So if u is first, u squared minus a squared, that's different than a squared minus u squared. And if we have that scenario, we use this trig substitution. There's three of them. I mean, this is it right here. Let u equal a secant theta. So these are the forms you're looking for, and these are the strategies you attack them with. Good luck.
Do we memorize them?
And I think you should memorize that. Yeah.
Memorize the whole book.
We will definitely make it. Okay.
Would you learn it better if I said don't memorize it?
No, I'm just making a comment.
Well, I'm making a comment too, and not to you, but to everyone. I don't know, would you learn it better? If I just said don't memorize this, but I'll write this on the board or something like that, I mean.
I think we would focus more on the application of the formula instead of the formula itself, which is kind of a bit more
The
important.
point, yeah, I mean, so, but you should do that anyway, but anyway, you're right. I mean, the idea is learn this process, and right, and memorizing it is one thing, but please, yeah, don't waste, yeah, right. Anyway, let's try another one. I'm sorry, let me see something. I'm sorry. Hang on a second. I'm sorry. All right, I'm making up one here. Dude, I'm not kidding you, dude. It's a good problem. Good problem here. Real good problem. I might not have time to do too many more. Let's see if we can do this one. This is good stuff. Now, first of all, I don't know. You got no other method at your disposal. And anything you've ever learned before today will not work. So it'd be cool if you convinced yourself of that instead of trying some crap that you thought might work. I don't think anything else works. I don't know. Maybe you could get, I don't know. I might be wrong about that, but yeah, but I don't think so. I think you need this method. So if you need this method, by the way, look at my notes. My notes said it has to look like one of these. But the truth is, these notes are kind of general. I mean, this radical can show up in a denominator, this like just happened here. And sometimes it's not even a radical. Sometimes it's, well, it's the radical cubed. I mean, in other words, this is a square root, but what if it was to the 3/2? Well, that still applies because that's a square root cubed. And actually, sometimes they do these problems where it's like squared. There's not even a square root there, but you can still, if it's this kind of an expression, this trig substitution will help you do the problem. So my notes are kind of specific, but I'm trying to make you open your mind and you can. So what I had on this one was this square root in the denominator. And anyway, but why am I pointing to this one? Do you know why I'm pointing to that one?
Because that's What's the one we're about to use?
Because it's, and why? Because it's an a squared plus a u squared. It's not minus, and it's not this other minus, right? It's a squared plus u squared, so it's this one. So first you got to understand that. All right, so now, what's my u? What is my u? And what's my a? What's my a and what's my u? I need to figure that out. A is 4, and what's u?
3x.
3x. Because that's u squared. Okay, so according to the rule, I'm supposed to let u equal a tan theta. So I got to let u, which is 3x, equal a, which is 4 tangent theta. Yep, that's what I got to do. That's me letting u equal a tan theta. See, I don't bother to call something u. I mean, I don't really want to go u is 3x, so du is 3dx. Let's turn this into u, then do a trig. You with me? I'm not doing that. I'm skipping. I'm just temporarily calling it a u to fit the formula, but I'm not doing a u substitution. I'm doing a trig substitution. That's my u squared, that's my a squared, and there I go. Okay, here we go. What's the first step after you declare the correct substitution? What do? You take a derivative right here, because you need dx and d theta. So here we go. The derivative here, please. 3dx. That's how you do that derivative. 3dx equals, on the other side, how do I do that derivative?
4 secant squared
4
theta.
secant squared theta d theta.
Yep. You know, I think I'm going to replace this dx. If I'm going to replace this dx, maybe I want to solve for dx. If I want to solve for dx, what should I do? Divide by 3. So dx is 4/3 secant squared theta d theta. All right, I'm going to start replacing all this crap. Here we go. What about the 8?
Pull them out.
I could pull it out or leave it. Right, okay. The 8's out front. That leaves a 1 up there. What about the dx?
4/3 secant.
There it is, 4/3 secant squared theta d theta. And what about this crazy radical here? Well, it's a 16 plus, all right, I'd like to do some of this in my head. Look, you guys, this was my u squared, right, you guys? Right? Yeah. And then this was my u. So my u is this, so it's, so that, right? So it's that thing squared. So it's 16 tangent squared theta. See, the reason that you want these 16s to match. Because what's the next step? You factor out a 16. Now I'm gonna mess with this radical a second, you guys. I should just go to my scrap paper, but I'm messing with this radical. I'm factoring out a 16. It's 1 plus tangent squared. What's 1 plus tangent squared? Secant squared. What's the square root of 16 secant squared? 4 secant theta. I mean, the point of the trig substitution was sort of to clean up the radical. And it did. It did it again. It did it last time too, when I did with my sine substitution. This time it did it with a tangent substitution. Now I'm a little disorganized here. Here, I better get organized. Hang on. I'm a little bit disorganized over there. I hope you're not lost. There's an 8 out front. If this 4/3 secant squared theta, it's off to the side here, but if you don't mind, I'll just put it in the numerator here. And then that radical was in the denominator. And what did the radical just turn into? 4 secant theta, right.
Yeah.
So that's in the denominator. You know what, when I look at these problems, listen, I feel like these problems kind of have these 3 stages. And stage 1 is, can you handle this substitution? Can you get it all replaced? Clean it all up, and it turns into a trig integral. And so stage 1 is over. Whew, good job. Stage 2 is, okay, now it's a trig integral. Can you integrate it? Good luck. and then it's integrated. We'll do that in a minute. And then stage 3 is, oh, now we got to turn the answer back into x's. And maybe I got to draw a triangle, and so there's these 3 major stages of doing these problems. I kind of think of it like that. So hopefully you followed stage 1, and here I am. I'm going to clean this up. You know, the 4 can cancel with the 4. I can pull the 1/3 out. I think this is an 8/3. Oh, I can cancel one of those secants. So I think that's what this is now. I canceled the 4. I pulled the 1/3 out. I canceled the secant. Now, can we integrate a secant?
Yes.
Secant's kind of weird.
ln
It's the ln
absolute value
of secant theta plus tangent theta, right?
Yeah.
Plus c. Woohoo, we're done. Well, no, wait a minute.
Got change in value. Wow.
All right, so here we go. To turn this back into x's, I think you go back to the original declaration, and what I do is I solve for the trig function. So I divide by 4. So can you see 3x over 4 is tan theta, right, you guys? Divide by 4 right there. 3x over 4 is tan theta. I want to draw a picture of this angle. There is an angle in a right triangle. There's an angle who has a tangent of 3x over 4. So if I do that, 3x over 4, that's opposite and adjacent. Then I can do Pythagorean Theorem that says square him, add it up, put it on the hypotenuse, and take a square root. Right? So it'd be the square root of 16 plus 9x squared, which was an expression in my original problem. That tends to happen. It doesn't always, but it tends to happen. But now I can stare at this triangle and fill this crap in, I think. Here I go. 8/3, the natural log of secant theta. What is secant theta? Secant theta is the reciprocal of cosine. Cosine would be adjacent over hypotenuse. So secant must be hypotenuse over adjacent. Yeah. So here comes the secant of theta. It's the hypotenuse over the adjacent. Plus the tangent of theta. The truth is, I can see it in the triangle, but it is stated right here. The tangent of theta is 3x over 4, but it's there, it's adjacent, opposite over adjacent. Wow. And we just integrated this nasty thing we just integrated this problem. U substitution doesn't work. Good old-fashioned U substitution doesn't work. What works is trig substitution. This specific trig substitution is what worked. And we got our answer. It's a process. It's a hell of a process. I like it though. It's trig substitution. You can practice some 8-3 homework, which is doing trig integrals, but I think the point of 8-3 homework is so you can do 8-4. What happens in 8-4 is you have these problems that get turned into trig. And so then you end up trying to integrate some trig. So if I was you, I don't know, you get 8-3 practice when you're up in 8-4. Because you do trig substitution, you turn these into trig integrals, and you try to do them. So I don't know. You can practice a little 8-3, but I'd try getting into 8-4 if I was you. The beginning of the homework is nice. They tell you kind of what to substitute. They're kind of nice to you at first, and then it's up to you to kind of figure out what is the pattern and what's the substitution. But at first, they're telling you what to do at first. So I only did 2 good examples, but I think I'll quit today. So start pushing into 8-4. You still like chapter 8? Is that?
No.
Both structure law and the stress theory at the same time.